All right, hello. I'm going to do a video here about basic algebraic maps, which I guess you can think of as a part two for the basic algebraic structures video I did a little bit ago. Um, so since it's been a little while since I recorded a video, let's recall some of the things I said last time or the time before. So a function between two sets we defined to be a relation, and a relation we define to be a subset of the Cartesian product x cross y. So it's a subset of the pairs of elements, one coming from x and one coming from y. And a function is a special type of relation so that for all x and x, there's a unique y and y that's related to x. So I gave the example of a function from R to R, which is the only kind I can really draw a picture of. Right, it's a function if it passes the vertical line test. Maybe I should draw it in a different color. So if there's a unique y value for each x value, then it's a function. Okay, and that's what we talked about in some previous video. And then we also defined some very important things you can talk about with functions. One of them is injectivity. A function is injective if whenever your two y values, f of x and f of x prime, are equal, you must have the x values are equal. For a function from R to R, that's the same as passing the horizontal line test. So for example, a function like this is not injective because here's some f of x and here's some f of x prime, but x and x prime are not the same. But a function like this is injective because it passes the horizontal line test. Okay, so that's injectivity. And then a function is surjective or onto if for every y and y, there exists an x in x so that f of x equals y. So for every y in the codomain, there exists an x in the domain that hits it under the map f. And then we defined a function to be bijective if it's both injective and surjective, if it's one-to-one and onto. And a fact, I don't know if we proved or not, but a function is bijective if and only if it has an inverse. And I think I'll say one really quick remark. We have these special functions called ID from x to x between a set and itself that just takes x, each element x in x to itself. So it's an invisible map, it does nothing. And an inverse is defined to be another function such that f inverse composed with f. So this is like the identity function on x, right? Each set has its own identity function. F inverse composed with f should be the identity on x, and f composed with f inverse should be the identity on y. Got that right? Yes. Okay. So that's what we mean by an inverse of a function. I think we'll say more about it in the next video, but we have identity functions and we have this property of an inverse function, and you always have an inverse function if your function is bijective. Okay, so now let's talk about the actual topic of the video, which is algebraic maps. So last time we defined algebraic structures by saying that they're sets that have some sorts of algebraic operations on them, and the kinds of different operations tell you what kind of algebraic structure it is. A map between two algebraic structures will be a function that happens to preserve that algebraic structure. So it preserves the operations that we put on the set. And then we'll say that it's a morphism of whatever kind of structure, and an isomorphism will just be a bijective morphism in every case. Okay, so first example and easiest is group homomorphisms. So remember that groups were sets with one operation on them. So a group homomorphism is a function, let's say G and H are groups. I'm going to denote the operations by different symbols, just so that we can keep track of where the operation is happening. And then I'll stop doing that later because it's annoying. A group homomorphism from F from G to H is a function from G to H as sets, such that F of G plus H equals F of G dot F of H. So this is the operation in G, this plus, and it gets transferred to the operation dot in H by the map F. So F is operation preserving. It preserves the group structure. Then it's a group homomorphism. And if it happens to be bijective, then we say it's a group isomorphism. So let's do a couple examples. The identity map, this is going to be an example for everything, so I'm going to stop writing it after this one, but the identity map is always going to be, it preserves every kind of structure, right? Because the identity on G plus H is just G plus H, that's the definition. And then G is the identity on G, and then H is the identity on H. So it's basically tautologically always a group homomorphism. Okay, and then here's a non-trivial example. Remember that Z was an abelian group, the integers, and we had an identity, which was 0. We didn't have a multiplication, but if you have an abelian group, you can always define, I think I mentioned last time that abelian groups are the same thing as Z modules. So you can always multiply by integers, because if I have an element G in G, I can take an integer n and multiply it by G by just taking G and adding it to itself. I didn't clarify what our operation on G is. Let's say that we have G plus. Then I just do whatever the operation is I have in G to itself n times. That gives you a Z module structure on any group. So in particular, what I mean by 2n is n plus n in the group Z with the operation plus. Okay, so there's no ambiguity in what that means. All right, so why is this a group homomorphism? Well, because if I have m and n, two integers, let's just check the property. F of n plus m, that's the operation in Z. It equals 2 times n plus m. Well, by definition, this is n plus m plus n plus m. And Z was an abelian group, and its operation was associative and commutative, so we don't have to worry about parentheses or anything or order. This is just 2n plus 2m, which is f of n plus f of n. So check. This is a homomorphism of groups. Okay, let's do one more example that's also pretty trivial. Take this homomorphism from Z to Q. So remember, Q was also a group under addition, and we'll just send n to n over 1. And notice that this map is also injective. So I claim that it's pretty obvious that this is a group homomorphism for the same reason that the identity is, because f of m plus n equals m plus n over 1, which equals m over 1 plus n over 1, which equals f of m plus f of n. So this is definitely a group homomorphism. This is a injective group homomorphism, but it's not surjective. So let's check that it's injective, just for fun, because we haven't checked that anything's injective yet. And might as well. Okay, so suppose, well, okay, if f of m equals f of n, that means that m over 1 equals n over 1. Multiply by 1 on both sides, it means that m equals n. So it's definitely injective, but it's not surjective. Why? Because there is nothing in the integers that can, under this map, ever hit 1 over 2. And I claim that's kind of obvious, right? If n maps to 1 over 2, well, it just can't happen. F takes n to n over 1. So there's nothing that does that. So we'll say that that 1/2 is not in the image of f, or the range. Sometimes we call it the range of f. Okay, anyway, that's just an example. Now let's make a remark so that we can prove one thing. So a group homomorphism always sends the identity to the identity. Let's prove it. So we only have one property, so let's go ahead and use it. By the way, so let me remind you, F was a map from G to H. And by EG, I mean the identity in the group G. And by EH, I mean the identity in the group H. Okay, so because EG is an identity, if I multiply it by itself, I should get itself. That's what it means to be an identity. But then F of EG equals F of EG times F of EG, whoops. F of EG times EG, and then because F is a group homomorphism, it has to respect the multiplication structure. So it has to map this to F of EG times F of EG. But then what if I move this over so that I can write more? Let's move it here. Okay, what if I multiply on the... let me move more stuff over. Sorry. I want to multiply on some side. Let's multiply on the right by F of EG inverse, right? Because H is a group and F of EG is some element of H. We don't know which one, but H is a group, so every element has an inverse. So I can multiply by F of EG inverse, whatever that is. And here I can multiply by F of EG inverse. And then I don't have to care about what order the parentheses are in here because the operation is associative because it's a group. But I'll go ahead and put parentheses here. I can move them wherever I want. F of EG times F of EG inverse, because this is something times its inverse, it's the identity. But this is the identity in H because these are both elements of H. And this is the identity in H. So what we obtain is that EH equals F of EG times EH. And then because EH is an identity, if I multiply it on the right by something, I just get that something back. So this is F of EG. So the identity always goes to the identity in a group homomorphism. That's just a easy consequence of the one property that you have. Okay, now let's do ring homomorphisms. So a ring homomorphism, now you have to respect both the multiplication and the addition. So remember the ring was an abelian group under the first operation. So R should be an abelian group under plus. And then dot should be an associative binary operation that distributes over plus. So, and similarly, S should be an abelian group under star, and cross should be an associative binary operation that distributes over star. So we have two operations in a ring. And a ring homomorphism should be a function which respects both of them. So it takes the addition or plus or whatever in R to the addition in S, and it takes the multiplication in R to the multiplication in S. And then there's one extra property. So by the by the remark, remember that under plus and star, R and S were abelian groups, so they have an identity. And usually, when we're talking about rings, we call them 0R and 0S. And by the remark, it follows that f of 0R equals 0S. But sometimes in a ring, we might also have a multiplicative identity, which we call 1. And we when R has a 1, we call R a unital ring. And if R and S are both unital rings, in order to be a structure-preserving map, we also have to map the unit to the unit. So this is a third property that you need if your rings are unital. You need the unit to go to the unit. Okay. And a ring isomorphism is a bijective ring homomorphism. Let's do one example of a ring homomorphism. So remember that we can have polynomial rings. If we have a ring R, then polynomials are things of the form a0 plus a1 x plus plus a2. I have to write slow so the pen doesn't lag. Plus dot dot dot. You can have as many terms as you want. I'm only going to write a few though. And these AIs should come from R. And I can define a map from R of x to R of x by taking a polynomial p of x and replacing all the x's with x squared. So this would map this polynomial here to a0 plus a1 x squared plus a2 x to the fourth plus dot dot dot. Okay, so let's check that it's an abelian group homomorphism under addition. So I can add polynomials and I can multiply them together. That's the ring structure. So f of p of x plus q of x equals so maybe now, okay. Let's be a little bit cavalier about it, right? We have this polynomial p plus q, and it's defined on x to be p of x plus q of x. But I'm going to skip this step just because it's annoying to write. It's not a very good reason, but whatever. Okay, so this is p of x squared plus q of x squared, which is exactly f of p of x plus f of q of x. And if I multiply p and q, now we'll actually show the steps. So this is pq of x squared, which by definition was p of x squared times q of x squared. And this is f of p times f of q. Okay, so it respects both the multiplication and the addition structure. These things can be a little bit tedious to check sometimes. And let's do one non-example just for fun. Remember this homomorphism of groups, Z maps to Z, where n goes to 2n. This was a group homomorphism, but it's not a ring homomorphism, because f of n times m equals 2 times m times n, or sorry, n, whatever. I'm going to write it in the same order for consistency. But this generically is not equal to 2n times 2m, which is what I would get if I did f of n times f of m. So this is not a ring homomorphism from Z to Z. It's only an abelian group homomorphism. Okay, I'm not going to say anything about field homomorphisms just yet, because we haven't really done anything interesting with them. But the other reason is they're just ring homomorphisms because fields are special rings. They're commutative division rings. So the definition of a field homomorphism is the same. It's just a ring homomorphism. But we'll show maybe later that all field homomorphisms happen to be injective. That's an easy fact you can show once you know something about kernels of maps. But let's move on to module homomorphisms. Okay, so remember, modules were an algebraic structure that lies over a ring. If you have a ring R, usually we'll have a unital ring R. Then we have R modules. There was a left variety and a right variety of R modules, depending on whether you multiply your ring elements on the left or your ring elements on the right. I'm just going to do the left R module case to shorten the video. But a function, and let me remind you what these two maps, with these two operations were. So plus, right, we had a binary operation, just like in all the other algebraic structures, we had like plus from m times m to m. And then we had this other operation of scalar multiplication that takes an element of R and an element of m and gives you an element of m. So there's this binary operation, and then there's this scalar multiplication. So just to remind you of those operations. And here we'll let star be the scalar multiplication in n, and times be the addition. Okay, so a module homomorphism has to respect the addition structure and the scalar multiplication structure. And a module isomorphism is a bijective module homomorphism. There was a special case of modules when our ring was a field. We call an F module a vector space, and we call F module homomorphisms vector space homomorphisms, or more commonly, they're called linear maps or linear transformations. They're maps that respect scalar multiplication and addition of vectors. So they're the structure preserving maps of vector spaces. It's just a special case of a module homomorphism. Let's do two examples of those. So this abelian group homomorphism, we already checked that it respects addition, but it also respects multiplication, because if lambda is in Z, right, Z has an obvious structure as a Z module, both because everything is a module over itself, and also because abelian groups are the same as Z modules. But f of lambda times n is 2 times lambda n. And this is all just multiplication of integers by more integers. So 2 lambda n, which is the same as lambda times 2n, which is the same as lambda times f of n. So this is a Z module homomorphism, this map that we've seen like 3 times. And then I wanted to do an example of a vector space homomorphism. So remember that R2 is an R vector space. And the elements are pairs of elements x comma y, where x and y are real numbers. I just want to remark that a linear map between R2 and R2 takes the form of a matrix, a 2x2 matrix, and we write that as a bookkeeping device. It does this, right? 2, 1, 0, 3 as a matrix multiplied by xy gives you this thing, 2x plus y and 3y. So 2x plus y in the first entry, and 3y in the second entry. And every linear map between R2 and R2 is represented by some matrix like this. And every matrix like this gives you a linear map. So they're very similar concepts. I think we'll go into that a little bit more later as well, but I wanted to remark on it now. And finally, our algebra, or let F be a field. Let's define an F algebra homomorphism. Let me clarify that this, right, we get a different kind of thing if we change the field. So and remember, an algebra has three operations. We have a plus. We also have a scalar multiplication. And then we also have an internal bilinear multiplication that goes from A cross A to A and B cross B to B. And now I'm going to stop writing all the operations as different symbols because I ran out of symbols. To be a structure preserving map of F algebras, I need to take the addition to the addition. So here, this one that I unhighlighted, and I'm highlighting again, this is the addition in A, and it has to go to the addition in B. And this is the scalar multiplication in A, and it has to go to the scalar multiplication in B. So, and then also the bilinear multiplication in A has to go to the bilinear multiplication in B. So that's an algebra homomorphism. Let's do one example of an algebra homomorphism and then be done. The example that we might use later is the evaluation map. So I can add and multiply polynomials, and I can also scalar multiply polynomials. So if I take a field and I take the polynomial algebra over that field, that's an algebra, an F algebra. And also F is definitely an F algebra over itself, because I can, right, it's already a field and I can scalar multiply elements of a field by a field. It's just the multiplication we have to begin with. And I can define this map that I'll call EV because it's evaluation by just evaluating a polynomial at 1. And this is clearly an algebra homomorphism. I wrote down all three checks there. You can look at those. You can evaluate at any element of the field and you still get an evaluation homomorphism for that element. So that's one example of an algebra homomorphism. Okay, I think that's all I want to say for now. So bye.